Okay, and for this second video, we're going to talk about inverse sampling. So that's about how we move from, well, one of the ways we can move from a standard uniform distribution to some other distribution of random variables. Like I talked about in the first video, we're going to assume that we can draw IID uniforms. So talking about how to do this, I'm going to say see video 1. Where we sort of went over how we might be able to do that. So we'll just say that we'll be able to draw standard uniforms. I think I motivated that okay, so you can look into any further details about that if you want. So for this inversion sampling method, what we're going to need is the inverse of f, where let me just add here that f is the CDF, that's a cumulative density function, of x. Right? And then the inverse of it, we'll write that as f to the minus 1 of x. And we'll also call this the quantile function, because that's what it is. And what that does is it solves that if we set f of x equal to u, some u between 0 and 1, then we can solve it for x given u. And I'll show an example of this in a few moments. Now I'm just gonna note here that I've actually lied a little bit. I'm just gonna add a star here for a comment. It's because actually what we need is the generalized inverse, which is written like this, where this is an arrow. But if f is strictly increasing and continuous, then this generalized inverse is the same as the quantile function. Okay. And I'm not going to go into too much detail about what this generalized inverse is, but it basically just catches a few edge cases where the quantile function might otherwise not work. So if we go to the method, the inversion sampling method here, see in step 1 we draw u, and I want you to think of this like we draw a random percentile between 0 and 1. And because it's a percentile, it might be intuitive to feel that it should be uniformly distributed, how probable it is that we take any particular percentile. For example, if it should be equally likely to get between the 90 and 95th percentile, or between the 50th and 55th percentile. So therefore it makes sense for now that we draw u. Then in the second step, we set x, that's the output we want, to be the quantile function of our u. Right? So that's the method. Now I'll try to go over the intuition for why it works. So if we look at the case of the standard normal distribution, I'm just going to do my very best here to draw its distribution function like this. Or, you know, it might also be called phi of x, right? And we can see here that it's 50% of the outcomes from standard normal distribution should be less than 0. So okay, so let's try and draw what inversion sampling does. Right. So let's just call this example 1. So suppose we draw our u and we get the value of 0.975. So over here we end up here, then we'll go over here until we hit the distribution function. So this is 0.975, and then we'll drop down here, and for the standard normal distribution this is 1.96 dot dot dot. So here x is equal to 1.96 dot dot dot. If we wanted another case, we could also look at second example here. Suppose we draw exactly 0.5, u equal to 0.5. Well, then step 1, we get our u is equal to 0.5. Then we go over here, see where we hit f of x. Then we drop down here, and then we have that x is equal to 0. Okay. So now I'm going to prove that this actually gives us the distribution of the x's that we want. So first I'll just note that for the standard uniform distribution, the probability that u is less than a is equal to a, for a between 0 and 1. And that's going to be handy in just a moment. So the proof, probability that x is less than or equal to small x is equal to the probability that, and what was our x? That was what we got over here. That's the probability that f minus 1 of u is less than or equal to small x. Well, what can we do over here? We can take capital F on both sides of the less than or equal to sign. Then we get the probability of u being less than equal to f of x. Well, then we can use a little hint from before, or the standard uniform distributions feature here, and then we get f of x. And that's the end of the proof. We've shown that the x's have exactly the distribution function that we wanted. And now I'm just going to go a quick example of this. So we have some continuous positive random variable with a CDF of 1 minus exponential function to the minus x squared. And the first thing we might note here is that the CDF is strictly increasing and continuous as e to the minus x squared goes towards 0, as x goes towards infinity, right? So we know that the generalized inverse is the same as the quantile function, and then we can look to try to finding the quantile function by solving this expression here. So let's just write that up. So we have that 1 minus e to the minus x squared is equal to u. And then if we isolate x, we'll get that x is equal to minus log 1 minus u. And then we'll take the square root of it. And you can work this for yourself. It's not that difficult, I think. And this is then the inverse CDF, or the quantile function. I messed that up. And that should be fine. Okay. Now I just want to add a small comment here, that this was the expression which we solved in closed form, but for a lot of cases you'll have to solve it numerically because there's no closed form. And for example, for a lot of famous cases like the normal distribution, there's going to be a lot of really good and fast approximations available. But if you're doing something a little bit more exotic, you might need to use something like Newton's method for solving this equation. And of course that might slow you down a little bit compared to if you had the closed form available. So we'll now do simulation by inversion. And first we'll just want to plot the PDF and the CDF of the distribution. So I'll just make a number line counting from 0 to 6 by increments of 0.01. It's a vector which is about 6,000 long. Then I'll get the values of the PDF and CDF at each point, and then I'll plot them. Again, I'm marking the code and pressing F9. Okay, just jump over here. So here we can see the PDF and the CDF of the distribution. Now we want to do the actual simulation. So first we'll set n equal to 10,000, because we want to simulate 10,000 random variables. Then Matlab has this nice function tick and tock, which tick starts the timer and tock stops the timer, so we can actually have a stopwatch on how much time it takes us to simulate our random variables. So first, in step 1, we get the uniforms. We see we're getting standard uniforms between 0 and 1. We're getting the 10,000 of them, and we're just getting a vector of them. So we also call them a matrix with only one set of columns, right? And if you're ever in doubt about the input, you can double click or highlight the name of the function and press F1, and it'll display the help function for the function. But okay, then after we have drawn the uniforms, we'll put them into the quantile function which we derived, and we'll get our x's. So I'll just mark the code and press F9. And we see it took about a 50th of a second. Okay, now I won't go over this code down here in too much detail, but what it does is essentially it plots a histogram with 50 bars and superimposes the PDF on top of it to see if they match. And we can see here that they match quite nicely, as we would expect.